Hello, I welcome you all to this another interesting screencast. The problem reads, draw the shear and moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so let's draw this and then label it, find the support reactions. So there we have the beam. Let's label this point, of course. We have A there, then we have B. Okay. So let me label this CD like so. So we have a distributed force like so, and then later on triangle in between. And when you look at this loading here, it is symmetrical. You expect also the reactions to be symmetrical. So we have a moment, couple moment at the very end there at C, which is also there at D. Okay, so this makes the problem in fact much easier, which you are going to notice later on. All right. Okay, so there we go. We have this from A to B, which is a 5 kips per feet. Right, we have a reaction at A, which is going to be just a vertical reaction. Let me write A somewhere there, and also B, I move it a little bit further so I have space for writing. Alright, so there we go. I have AY there, that's a roller. I have here BY and BX. And the dimensions are as follows. Okay, I have 6 feet, I have 10 feet, and I have 6 feet. So I'll have an equivalent force somewhere here, and this equivalent force is just a 5 times 10, which gives me a 50. Okay, 50 kips. And this is acting at half the length of 10, which is just 5 feet. Okay, let's now find the equivalent force on the sides. We are going to have force there. Let me calculate it down. Here is half times the length, 6 times the load here, which is a 5, right? So this gives us a 15, right? A 15 kips. Is that so? This is 15 kips. Okay. Yeah, this is a 15 kips. And it's acting. This is 15 kip. And it's acting at this point. This point is equal to 1/3 of 6, which is equal to 2 feet. Right, this is 15, right? 5 times 6 is 30, by half is 15. So we have the same value this side. Okay, so this is a 15 kip. All right, and this distance also is the same. It's also 2 feet from B. All right, so with that information, let's dive directly and begin to calculate the values of we start drawing the shear and the bending moment diagram. All right, shear force diagram, bending moment diagram, plus and minus, plus and minus. All right, at C here, okay, we said let this be a C, okay, let this end here be a C, then there be a D, okay. So we know that at C, we don't have any concentrated load, that's where the distributed starts. And where we have distribution, when the load, in this case, the load is negative and is increasing, therefore you expect the slope for shear to also be negative and increasing, okay. All right, so here we are going to expect, let me draw these lines that just demarcates this boundary like so, and also here like so. All right, so we are going to have this behavior like so here. All right, negative and increasing. All right, up to there. So we can calculate this value here, and this value is just the area under the loading, the load diagram. So we already know it's 15, right? Because it's half times 6, the length, times 5. This gives us a 15. So this value is 15 kip. And then at A, here we have a concentrated load, which we need to calculate. All right, it's like I thought I'd done this, so let's do that quickly. At A here, I'll take moments about A, okay, summation of moments about point A equal to 0. All right, what do we have? We have a 15 times 2, 15 times 2, and then we have a minus 50 by 5, then we have a plus 15, this couple moment, all right, and then we have a plus by 10, and then we have a 15, that's clockwise, a 15 by 12, then finally we have a minus 15, this is clockwise, equal to 0. Therefore our by is going to be equal to 15 by 2 minus 50 by 5 plus 15 minus 15 by 12 minus 15 divided by 10. This is equal to 40, and then we have summation of forces in the y direction. We have a minus 15 minus 50 minus 15 plus ay plus by equal to 0. We already have a by, which is this one here. Therefore, my ay is just going to be equal to minus 15 minus 50 minus 15 and then plus 40. Yeah. So this gives us a minus, a 40 rather. Okay. 40, right? Minus 15 minus 50 minus 15 and then plus 40. Okay, so ay is also equal to 40, and then summation of forces in the x equal to 0. Bx is equal to 0. So we've calculated these values. This is 40, this is 40, this is 0. All right, let me get rid of this. Okay, so we had started doing the plots here. Let's continue. So we are saying at A we have a 40 kip, we have a 40 kip, so it means this 15 is negative 15, this is a negative, will be reduced by 40, so it will be 15 minus 15 plus 40. What does this give us? Gives us a 25, right? So this is going to be equal to 25 kips. So we expect this to rise from here We expect a rise of up to 25, maybe let's say somewhere there. So let's name this point as 25, 25, keep. All right. And then from that point, we have a distributed again in between. So this is our loading itself is it is negative, okay, and it is constant. All right. Therefore, the slope, we expect it to have a negative constant value, right? So let's find the value at the far end there. This is 25. So we have 25, positive 25, okay, minus 5. 5 keeps per feet. So let me remove this. Remove this so that we are not confused. Okay, this we need to remove them. We don't need this when we are doing the plots. We just needed this information for our support reactions. All right, we remove them so that our figure is clean. Great. There we go. Something like that. Okay. Okay, so we have 15 kips. 5 kips times, so 25 minus 5 times 5 times 10. Okay, what do we get? 5 times 10. So we get a minus 25. All right. So we expect this point maybe to go up to somewhere there. All right. How many units? 3, 1, 2, 3. Okay, up to somewhere there. This point there. So a negative, we said negative constant slope. Okay. Where is it? Okay, something like this. I want a green. Okay, they are like so. So this point here is 25 kips. Okay, so at this point we have a concentrated load of 40. So it's minus 25 plus 40, and this gives us a 15. So expect a 15 up to somewhere there on top. Let's say somewhere here. All right, somewhere there. Okay, somewhere there like so. So this point is a 15. This is a 15 kips. Then from 15 we have distributed load. So our loading is a negative, and is decreasing, right? So we expect the slope for shear to be negative and decreasing. Okay, so it can only decrease like so, and let's find the value. So we have a 15 minus 5 half times 5 times 6. So this is up to 0. So this will go up to 0 and close up like so. Right, so that point is 0. So I think this is about it. We have negative, we have positive, we have negative, and we have positive. Okay, so let's draw the bending moment diagram. Let's just move it a little bit down, maybe somewhere there like so. I hope it will fit. It has to fit. We have no choice. All right. So this is the shear force diagram. And when you look at this, the pattern is similar, okay, about this point, okay, this axis in between A and B. Pattern is similar, it's just the mirror, okay. So the moment, let's do the plots for the moment. The moment we're going to use the relationship between our shear and our moment. So we know that from C to A, the shear, okay, the shear force itself is negative and it is increasing. All right, and therefore we expect the slope for the moment to be negative and increasing. All right, let's do that. Negative and increasing. Let's bring it somewhere there. All right, so at this particular point we do have a value of 15 kips, 15 kip feet. So imagine again, we cannot use this value directly. Imagine we do a small section here, and if it is small part, and if we did so, the internal moment here is going to be in this direction with the same value 15. Okay, the one applied is in that clockwise direction. The one that we get when we do an infinitesimal cut to the right of C will be in the clockwise direction, which is negative. So let's imagine we have a value here of 15 down, which is negative, 15 somewhere there. Okay, so let's say this is where we are starting from. All right, so we are starting from here, and that value is 15. This is 15. This is 15 kips. 15 kips feet. All right, and then we are saying our moment is going to be negative and increasing. So from C here to this point here, we need to find the value of this particular moment, the value. Since our load is of degree 1, polynomial of degree 1, our shear is a polynomial of degree 2. We expect our moment to be a polynomial of degree 3. So we need to find the shear function so that we find the value of the moment at A. So we can do that. So we know that our shear, okay, is going to be equal to minus, of course, this is minus value, minus half times so we have done the section. It's as good as just doing the section. This is what we are doing. So the section for that, this is what we are doing. This is the section. We are just trying to find this shear. So over the distance x, so this is equal to the slope for this, the function for that q of x is going to be equal to the gradient. To us, the gradient is 5 divided by 6, right, x, okay, and the loading therefore becomes equal to half times 5 divided by 6x times x, which is equal to 5 divided by 12x squared. Okay, is that fine? Great. And then we have a v there. Therefore, summation of forces in the y, we're going to have minus, so summation of forces in the y, we have minus v. Of course, we have also a moment there, but we are not interested in the moment. Minus v minus 5 over 12x squared equal to 0. Therefore, v is going to be equal to minus 5 over 12 x squared. So this is a function that governs our shear. Okay, so a function that governs our shear. So we expect a 15 if we are to plug in a 6 in there. So we have minus 5 over 12, then times 6 squared, we have a 15. Okay, so we're going to use this to quickly do the integration. Let's do that. All right, to find, because we know the area under the shear loading or shear diagram itself gives us the moment. So moment at A, so we say moment at A is going to be equal to integral from 0 to 6 over this shear diagram minus 12x squared dx. So this gives us minus 12x cubed divided by 3 by 12 is 36. And then let's plug in our constant 0 to 6. This gives us minus 5 times 6 cubed divided by 36. So this gives us a minus 30. So we have a minus 30, right? So this is going down. Let me move this somewhere there. Space is quite limited. Okay, let me reduce this. Okay. So let's say it is somewhere there. So this is our 15. I mean, this is our, yes, 15 kips. This is our 15 kip feet. So the value that we are finding is a minus 30. So a minus 30, in fact, this one is plus the moment at A, which is a negative 15. So this final moment at A gives us a minus 45, right? So this is going to be a 45 instead, minus 45 kip feet. All right, and then we've been told it's negative and increasing, so we expect this to be something like so. Negative and increasing, it's going to be something like so, right? Like so, right? Something like so. And then in between, and then we have a portion that is positive from A to half the length of 10 from A, that is from 6 to 15. I mean, from 6, yes, from 6 to 11, right? That's half of 10. 6 feet to 11 feet. We have a shear there. Let me write down. So we have shear. Shear is positive and decreasing. Therefore, slope for moment is going to be positive and decreasing, right? Decreasing. Okay. So this value there, this is half. Okay, the length. So we can calculate this, and then this one is just going to be our the moment here. It will be of degree 2. The quadratic function is positive and decreasing, so we expect it to go up. How much up? Let's calculate how much value it is. Let me wrap this. This is going to be equal to 1 over 2 by 25 by this is half. This distance is half here. From there to there, this is 5. So times 5. So this is equal to 0.5 times 25 times 5. So this gives me a 62.5. Okay, which is positive. Right. So we expect this value to rise. So say 45 minus 45 plus 62.5. Okay. So it gives us a 17.5. So it will rise up to somewhere, let's say there. Okay, so there. Okay, so we have this behavior where we have a positive but decreasing. It's a quadratic, so we'll have this behavior like so, like so, like so. All right, and since the other part there has a similar behavior, okay, because this is symmetrical about this axis, okay, so we expect this also to take the similar shape. We expect this to take a similar shape. Here shear is negative and increasing, therefore the slope for this also will be the same. From here, if you did the calculation, so the second part there we have shear negative and increasing. We expect slope for moment to also be negative and increasing. Okay, and the value for that moment, what did we say this value is? We said this value is 17.5 cube feet, right? 45 minus 62.5, right? 17.5. Okay, 17.5. Right, so it's negative and increasing. So if you calculated this value also, it's going to be equal to it's a negative value that moment. It is also the same similar value to only be negative. It will be 62.5, right? Because we are calculating is 25 by 5 by half, which is equal to 62.5, and it's negative, so we have 17.5 minus 62.5, which is equal to 17.5 minus 62.5. This is equal to minus 45. All right, so this is going to go down up to somewhere here. All right, somewhere here. So it will repeat the same fashion. So this will come down. It is going to come down. I use green. Where is my green? This is going to come down like this. Okay, it's supposed to be the same fashion. Oh Lord. Okay, something like that. And then from there, so this point here is 45. This point here is 45. 45 keep. And then from there onwards, we have this behavior here where our shear here, our shear there is positive and decreasing, positive and decreasing. It's positive and decreasing. We expect the same there. Slope for moment it will be positive and decreasing, right? And this value there, it will not be different from the other one there. If we calculated that, we did the integration, it is similar to the other part there. So positive and decreasing, it is going to close up at the very end there. So this will go up like so. No, sorry, it is going to go up like so, 15 somewhere there. And since we have this so we have this value here, which is clockwise, but if we did a section just to the left of D, we are going to have anti-clockwise, which is positive, which closes up this part. All right, it closes up this part like so. Okay, so this is 15 cubes feet. So this is negative, this is negative, This is positive. Right, this is about it really, and I hope the video is helpful. So from for the moment, from C to A, this is a polynomial of degree 3, and then from A to B is a polynomial of degree 2 quadratic, and then from B to D is a polynomial of degree 3. Okay. So basically this is the behavior, and I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue subscribing and sharing my channel. Bye bye, and see you in my next screen.